Okay, so 15.3 is some simple ways to work with equilibrium constants and equilibrium expressions. So far, we've just been talking about K at some value. How can we start to use its mathematical value to solve some interesting questions? Well, the first thing is that you can actually allow a reaction to reach equilibrium and then directly measure the concentrations of all of the different components and use that to find the value of K for a new reaction. So let's consider this reaction. Carbon monoxide gas plus H2O gas in equilibrium with carbon dioxide gas and hydrogen gas. This is one of those reactions that happens inside your catalytic converter in the exhaust of your car. And then the hydrogen would actually also combine to form more water in a second reaction. What would be the equilibrium expression for this? Kc would equal the concentration of CO2 times the concentration of H2 over the concentration of carbon monoxide and the concentration of H2O. So suppose you allow this reaction to proceed and you measure all of the concentrations. You find the carbon dioxide concentration. Carbon dioxide is 0.150 molar. And you find that the hydrogen concentration is equal to 0.300 molar. And the carbon monoxide concentration is equal to 0.0600 molar. And finally, the water concentration. This is water vapor, it's a gas, so it does appear in the expression and it will have a concentration, and that is 0.120 molar. Well, using these values, we can just plug them in and we can find the concentration, we can find the equilibrium constant. So CO2 is 0.150. And remember, this is one time I can be sloppy. I'll just leave off the molar. H2 is 0.300. Carbon monoxide is 0.0600. And H2O is 0.120. That's all going to equal Kc. So that's pretty simple math to work out. So we've got 0.15 times 0.3 divided by 0.06 divided by 0.12, and our answer is that K is equal to 6.25. K is equal to 6.25. And we have the equilibrium constant. We could go ahead and use that to solve all sorts of problems moving forward that involve this reaction. Even if the conditions are different than this particular example, now we have Kc, and that can be a value that we use in all sorts of problems. If we already know the value of Kc, then we could use it to solve for an unknown concentration at equilibrium. So here's another reaction. C3CO2H, that's aqueous, plus H2O liquid is in equilibrium with H3O plus aqueous plus CH3CO2 minus aqueous. This is the weak acid reaction of acetic acid with water. And KEQ or KC in this case is going to equal the concentration of H3O plus, and the concentration of CH3CO2 minus over the concentration of CH3CO2H, acetic acid. Water is absent from this expression because it is a liquid. And suppose we put some acetic acid in the water and we allow it to reach equilibrium, and I find that CH3CO2H concentration is 0.250 molar, and I find that the CH3CO2 minus concentration is equal to 0.350 molar, and I know that K for this particular reaction is 1.8 times 10 to the negative fifth. So with this information, I can find the H3O plus concentration. Let's just put it in. 1.8 times 10 to the negative fifth is equal to that unknown H3O plus concentration times 0.350 molar and divided by 0.250 molar. And again, I can afford to be a little sloppy with the units. This is unitless, I'll just have to tack on the molar units at the end. So let's solve this. I'm going to say 1.8 times 10 to the negative fifth times 0.25 divided by 0.35, and I get 1.3 times 10 to the negative fifth, 1.29 if we give us 3 sig figs. 1.29 times 10 to the negative fifth molar. Okay, so that's another pretty straightforward way that we can use the equilibrium expression to do some math for us. Okay, now let's consider how we can relate the equilibrium expressions of reactions that are simple derivatives of each other. So, for example, if I have A in equilibrium with 2B, I could make another reaction which is 2B in equilibrium with A. This is just the reverse of that one. We'll call this reaction 1 and this one reaction 2. Actually, I don't like that. Sorry. Those of you that took me for 1210 know that when I'm combining or manipulating chemical reactions, I like to label them in this way, put a circle around them. There's just so many letters and numbers flying around. I like putting a circle to sort of be a label for a reaction. And so what is the equilibrium expression for reaction A? That's going to be the concentration of B squared over the concentration of A. And what is the equilibrium constant for reaction B? That's going to be the concentration of A over the concentration of B squared. And what do we notice about these? They're just the inverse of one another. So Ka is equal to 1 over Kb. Or we could say Kb raised to the power of -1. So this will apply for any pair of reactions that are the inverse of each other, not just this simple example that I've given here. Well, let's look at a third reaction. We'll call it C. C is going to be 2A in equilibrium with 4b. Now, we could say that b is equal to kind of the reverse of, oh, let me write it down here. Okay. We could say that reaction B is equal to the reverse of reaction A. C would be equal to 2 times reaction A. We've just doubled everything. Okay, well let's just look at what KC is going to equal. That'll be B, oops, not squared, B to the 4th in the numerator, and A squared in the denominator. Right, we've got a 4 and a 2. How does KC relate to KA? KA is B squared over A. KC is B to the 4th over A squared. That is just KA squared. And so you see this exponent is kind of related to that coefficient. The -1 here is related to that coefficient of -1 there. And we can use these relationships now to figure out the equilibrium constant for more complex reactions by building them up from simpler reactions. This is all very similar to Hess's law, which we use to find enthalpies of reaction by reconstructing one reaction out of other reactions whose enthalpy was known. So that may not make a whole lot of step, but I just realized I need to do one more. Okay, so let me just erase all of this. Okay, suppose I have A in equilibrium with 2B, and then I have B in equilibrium with C. So we'll call this reaction A, and we'll call this reaction D, because that's a new one. Okay, and we know that Ka is equal to concentration of B squared over the concentration of A. Okay, and Kd, that's going to equal the concentration of C or the concentration of B. Now, what if I have another reaction here? I'll call it reaction star, just to keep it distinct. And star is going to be equal to A in equilibrium with 2C. Now, how can I reconstruct this reaction star out of A and B? Well, I would say that star is equal to reaction A plus 2 times reaction B. Right? Again, this is kind of going back to some skills you learned in working with Hess's law. Well, what is going to be K star? And that's going to be the concentration of C squared over the concentration of A. But can we express this in terms of these equilibrium constants we have here? Well, let's just try to reconstruct it. I need an A in the denominator, and that only comes from Ka. So we've got a Ka, and let's keep track of what we have so far. Ka gives me an A in the denominator and a B squared in the numerator. What else do I need? I need a C in the numerator. That can come from Kd squared. So we'll do Kd squared, because I need to get a C squared. What does that give me? That gives me a C squared in the numerator and a B squared in the denominator. And the B's cancel out, and we see that we're left with C squared over A. That's what we want. So K star is equal to the product of Ka and Kd squared. And if we come back here to my formula, where I accidentally wrote a B instead of a D, we know that the reaction A is composed of reaction, or it can be recreated by taking reaction A and 2 times reaction D. So we see that when you add reactions together, their equilibrium constants are multiplied together. So if you reverse a reaction, then you invert the equilibrium constant. If you double or triple a reaction, then you square or cube the equilibrium constant. If you add 2 reactions together, then you'll take the product of their equilibrium constants. Okay, let's finally just do one grand example. We'll use real world values. Okay, so I want to find K for this reaction. I'll call it reaction star. And that is N2 gas plus 2O2 gas in equilibrium with 2NO2 gas. And I need to recreate this reaction from 2 reactions that I know the equilibrium constant for. So N2 gas plus O2 gas in equilibrium with 2NO gas. This has a K value of 2.0 times 10 to the negative 25th. Is that in frame? Yes. And the next one is 2NO gas plus O2 gas in equilibrium with 2NO2 gas. And the equilibrium constant for B is given, and it is 6.4 times 10 to the positive 9th. So can I come up with a formula to reproduce equation star? Well, let's see. I need a nitrogen on the reactant side. That can only come from A. And I need 2 NO2s in the denominator. That can only come from B. And let's just make sure everything else adds up. We'll have 2 NO canceling out with 2 NO there. Our oxygens will add up to give us 2 oxygens. And so this is a pretty straightforward formula. What will be K star? Oh, there we go. Drew my star wrong. What will be K star equal to? It will be equal to the product of Ka and Kb, because they were added together to recreate that reaction. So what is the product of 2.0 times 10 to the negative 25th times 6.4 times 10 to the 9th? Let's figure it out. 2e negative 25 times 6.4 e positive 9. We get 1.28 times 10 to the negative 15th equals 1.28 times 10 to the negative 15th. That is our new equilibrium constant.